Hello! Today I'm going to talk about CDs, DVDs, and Blu-ray discs. This is a continuation of my previous video on LaserDisc where I talked about the basic technology, and today I'm going to talk about how they're manufactured, about how it evolved into CDs through Blu-rays, and a little bit about how the data is stored. That's getting us a little bit into digital electronics, which is for down the road in the digital electronics class, but I will talk a little bit about it because we need to understand how the CDs work. Just a quick review, the LaserDisc is an analog technology where we have a disc with pits molded into it, and I will represent those as different lengths of ovals here. And the rear surface of the LaserDisc is coated with aluminum so that it's reflective, and as a laser scans across here, as it moves from the high area called a land to a pit, there's going to be a change in the reflectivity, and so the pickup is going to pick up a spike, either going positive or going negative depending on which end of the pit that it's going into, and this is read by the electronics as the beginning of a signal, which I will explain in a little more detail in a moment. The LaserDisc was originally totally analog, and so the information was variable in length, which represented variable voltages. So for example, the TV signal would have a voltage that's varying up to a frequency of 4 megahertz, so very, very high frequency. Plus we had an audio signal which was much lower frequency, which would be up to 20 kilohertz. And essentially the information was encoded such that the distance between the centers of the pits encoded the video information. So center to edge is about the same. So if we take here to here, that distance is going to represent a particular voltage at a particular moment when it was sampled in making the signal for the LaserDisc. And the length of the pit, so here's two different lengths, a little bit drastic here, but the length of the pit represented the instantaneous voltage of the audio signal in the early LaserDiscs. So it was totally analog, where the distance between the pits represented a voltage for the video, and the length of the pits represented a voltage for the audio. Later, seeing that there is a huge amount of bandwidth available, they were able to modify this so they could put digital sound in there, which I will explain a little bit about that momentarily. I don't know exactly how they did it because they had to do it in such a way that it was still compatible with the analog players that could not play the digital discs, but somehow they cobbled in information into the audio signal such that it could be read as an analog audio signal for one channel of analog audio, or it could be read as two channels of digital information for stereo sound, and some other information could be encoded in there also. But that's the basic idea of how the information was encoded. Now let's talk about how these were made. They used a photo engraving process, which is something I'm fairly familiar with because I worked as a photo engraver for a couple of years. And to let you know what we did and how that can relate to how these were made, we made presentation plaques from brass, and we made printing plates and embossing dies from magnesium. And the process we used to make the presentation plaques, we would start with a piece of brass. So there's a square piece of brass that will become the presentation plaque. And we would coat this with a material called KPR. That used to stand for Kodak Photoresist, but they sold off that product to somebody else and they just called it KPR after that. And this is a material that looks like a lacquer. It can be sprayed on or spin coated. Spin coating means we spin it really fast and put a few drops of it on there and it spreads out very evenly. We actually spray coated, but spin coating was used for LaserDiscs and CDs, etc. And so coating it with this resist, and what the resist did is it would resist acid. That's why it's called resist. And this particular photoresist we used, KPR, was photo hardening, or was photo negative, meaning that before it was exposed to light, it could be washed off the brass with a solvent. But once having been exposed to ultraviolet light, it would harden and the solvent would not remove it. And so we would make a negative, And I'm going to just draw two letters on here. Here's our exciting presentation plaque with the letters AB on there. We would take that original image we wanted on the plaque and make a negative of it and lay it on top of this photoresist. So now we have a negative where we have black where we don't want the image, and the A and B would actually be light visible through the negative. And we would put that on the brass and expose it to ultraviolet light. And that would harden the resist where the light struck it, where the letters are. So now we end up with you could actually see a very faint image of the hardened solvent. And we would put that in a spray degreaser and spray a chemical called trichloroethane on it. It's a kind of a nasty chlorinated fluorocarbon, which has been banned since I did this. I don't know what they would use today, but we sprayed it with that solvent, and that would wash off all of the resist except that which had been hardened where the negative allowed the ultraviolet light to come through. So now we had this acid-resistant material on top of the brass. We would then put it in an etching machine, which had a conveyor that would pull the brass through and spray a chemical called ferric chloride on it, a rather nasty chemical that you don't want to get in your clothes. It left horrible brown stains. But actually ferric chloride is used in water treatment. They mix it with the water and it causes solids to collect and fall to the bottom. And they remove the ferric chloride after that, of course, and that's just another use for ferric chloride. Ferric chloride is also used for etching circuit boards, among other chemicals, because it etches copper very well. So now we have that etched, and so if we look at it from the side, we have the brass, which was like this with the resist on top. There's some resist there and some resist there, and the ferric chloride etched down, leaving raised portions where the resist was. And since these were presentation plaques, usually we would spray paint it black and then sand it, sanding the paint off of the tops of the letters, and we'd end up with a black background and a brass foreground. We would then coat that with lacquer to protect it from corrosion and mount it on a piece of wood, and there's your presentation plaque. The only difference is in the printing plates and embossing dies being made on magnesium. First we bought pre-coated magnesium. We didn't have to coat it with resist ourselves. The exposing process was the same, but the difference was we etched those in etchers which had them face down over a bath of nitric acid and a soap-like material, and it had paddles, these long linear paddles that would splash that acid soap mixture onto the plate. And the reason for that was that the combination of acid and soap would cause it to etch down at an angle, leaving some supporting material behind, and that would make the right shape for the embossing dies to give the angled impression in the paper when it was embossed, or if it was a printing plate, it left enough material to support the part that printed. So that's the photo engraving process. So here's how that relates to making a LaserDisc or CD, DVD, or whatever. They start out with a piece of glass that is polished very flat and very smooth, and this is then spin coated with a resist, but this is a positive resist. It works backwards from the negative KPR, in which case when the resist is first put on, it will not dissolve in the solvents they use to develop it, but once light hits it, places where the light hits will dissolve. So we start out with a glass master, and a laser is turned on and off to expose the resist where we want these pits, and it makes a spiral groove. I'm assuming that this probably spun much slower than it did when it was being read in the LaserDisc player, but it could have gone at full speed. I don't know. I'm assuming it probably went slower, and they could probably get more accurate spacing of the pits if they did that. So it's going to expose the resist wherever they want a pit. So, and it continues out in that spiral track until it's completely exposed. Then they would wash this with a solvent that would remove the resist where the laser had hit. So it's the opposite of what we did. The negative resist we used would be removed where the light did not hit. This is removed where the light does hit. So now we have that material. Here's our glass, and here's our resist on there with spaces where the pits will be. And then that is exposed to a very nasty acid called hydrofluoric acid. We never etched glass in our shop because the hydrofluoric acid to be used in a commercial scale would be just too concentrated to be safe. It's very terrible stuff. If you get it on your skin, you won't even know it. It'll go down straight to your bone and start eating at your bone and damage your bones without you even knowing.
When hydrogen fluoride mixes with the lovely liquid inside of your lungs, that creates hydrofluoric acid, and that, my friends, is not the way that you want to die.
And so we just would not use hydrofluoric acid. You can get very weak solutions of it to etch glass in hobby stores, but that's a very weak solution and considerably safer, but I still don't like it because I know how dangerous it was. But nevertheless, that's what you need to etch glass is the hydrofluoric acid, and they'd etch it through, and that's going to etch away where they want the pits. So the positive resist was weakened by the light. It was then washed away with solvent, leaving a space where the acid could reach the glass, and the glass would etch away where we want the pits. And this would make the master from which they would mold LaserDiscs from. And the same process is used for CDs, DVDs, and Blu-rays. Now, one thing that might be a little confusing, if I get this out of the way here, when they made vinyl records, they used a negative master to mold a positive record. In other words, the master of a record would have hills where they want the grooves in the record, and that would be pressed into the record, leaving, if we take the record here, leaving grooves in the record. So we had a negative and a positive. Negative was the master, positive was the molded record. It's backwards with LaserDiscs, CDs, and DVDs because of the way they're read. So this is put into a molding machine that injects hot molten polycarbonate plastic in there. And that's going to go in. They're going to clean the resist off first, of course. Let's get that resist off of there. And they put in the polycarbonate, and that's going to go down in just like the vinyl record, except since the disc is going to be read from the opposite side, so the laser comes in the back side. So once this is removed from the mold, let's get the master out of the way here, it will then be coated with aluminum and is going to be read from the opposite side. So this is coated with aluminum, then it will be coated with a thin layer of lacquer to protect the disc, and if there's a label on it, which usually is, will be imprinted on top of that lacquer. So we had the master, let me try to redraw that here, and where there was a pit in the master, now from the reading side we have a pit in the surface that's being read, coated with aluminum, coated with lacquer, then a label, and notice that the data is on the label side. So where do I have a CD? Here's a CD right here. So here's a CD right here, and here's the side that you read from, so the laser comes through this side, but it actually has the data on this side. So we mold the data in, coat it with aluminum, put a label on it, and so the data is actually on the label side, and the other side is where we read from, going through the polycarbonate disc. So that's the basic idea of the manufacturing, where we can mold these over and over again, starting from the master. So it's a physical process that the master is made, and many, many discs are molded out of that master. Now, I got a little ahead of myself here and talked about the CD with the layer of lacquer and the label on it. If this is a laser disc, what they're going to do, let me try to draw two of these here. Here's our laser disc. There we go. So there's our laser disc with the pits molded in. If I can get my drawing the way I want it there. Pits molded in, coated with aluminum, and then they would take another disc and they would cement it to the other side. So let's draw that over here. And totally unrelated material, so the pits and lambs are totally different. And I don't know if they put a layer of anything in between them, but they were basically, once they were coated with aluminum, they were cemented together, making a two-sided LaserDisc. So that could be read from both sides. CDs can only be read from one side. However, DVDs are made differently because we do have two-sided DVDs. So a DVD is made much thinner than a CD, and if it's going to be a one-sided CD, they glue another piece of polycarbonate to it and put the label on that. So the DVD is half the thickness of a CD, but they glue another half on there to make it the same thickness so that the DVD is the same thickness. Or if you want a two-sided DVD, this second side would actually have data in it and be pretty much like the two-sided LaserDisc. So two-sided DVDs are made like the two-sided LaserDisc, but your CDs were never made that way that I know of, and so they simply have the polycarbonate CD that was molded into the mold, layer of aluminum, layer of lacquer, and then the label is put on that. So we learned one important thing here is that the data is on the label side, so you want to protect that. Of course, it's protected with a good hard coating of lacquer. This side might get scratched, but it won't damage the data, and if the scratch isn't too deep, you can still read the data underneath. But if you scratch this side, you're going to ruin the data. Another thing you'll notice about CDs and DVDs, which you cannot see, is that they have at the center, here's the CD, here's the hole through the center, and around that hole is a little ridge. And that's to protect it when you put it on a table or something. So I really can't show this. I'll show a little video up here showing me with a DVD, and you can see that it doesn't quite touch the table because of that little tiny ridge that you can't see, but you can sure feel it. It's very, very tiny, but it's enough that you can feel to protect them from touching each other or touching a table. When they're stacked, they don't actually touch each other. When they're on a table, they don't touch the table, and that protects this surface from being scratched. And of course this one too, because that's where the data actually is. Blu-ray discs do not have that ring. Theoretically, they have a hard coating on them that resists scratches enough that they don't need it. I will have to take their word for that. So that's your basic manufacturing of your CDs and DVDs. Now let's look at how the data is put on them. Now, I already talked about the LaserDisc, which was originally all analog, where we just simply had the length of the pit or the distance between the pits was variable and carried analog information. But the CD is totally digital. So I'm not going to say as much as I might because that's for the digital class, but I'm going to give just the basics of how the data is stored on there. And if you look this up on the internet, you'll probably be misinformed, because when I wanted to find out exactly how the data is encoded on there, site after site said, oh, real simple, you're encoding ones and zeros, so you have to have two states. Therefore, a short pit is a 0 and a long pit is a 1. Well, that sounds logical if you don't know much about these kind of things, but that's not really the best way to do it. First of all, we have a problem. If we have a whole string of ones, they're going to kind of run together and make one long pit, unless we do something to prevent that. Well, that could be a problem, but in the end it's not, because it can be handled, and it turns out it's something we do want to handle. I'll talk about down the road. But the way this is encoded originally is a method called frequency modulation, or FM. What that means is if we have a string of zeros, we're going to start out with a square wave of a certain frequency. So there's our square wave that's going to be used to determine where the pits and lands are going to be on the CD. And if we have a string of zeros, we're going to have one frequency, and there's our string of zeros right there. Notice that each zero takes one half wave. And so you might think, well, digital, that's going to be a 1, that's going to be a 0, 1, 0. No, it's actually each half wave, if we have one frequency, is a 0. But if we have a string of ones, let's put a 1 here, a 1 there, a 1 there, there, and there. These look like tick marks. I'm going to make sure we know that these are numeral ones. There, we can see they're definitely ones. And so we're going to have something more like this. There's a 1, there's another 1, there's another 1, another 1, another 1, and another 1. And so if we have a string of 1s, we have double the frequency as we would with a string of 0s. So if this is 100 kilohertz, this will be 200 kilohertz. And the end result, once we put 1s and 0s together, is we end up with, well, I'm just going to modify this. Let's throw a couple of 0s in here. Let's throw a 0 in there and a 0 in there. And what that's going to do is that's a terrible drawing, but notice that it's going from low to high for 1, low to high, and suddenly it's high to low. I wanted to move that over here. Here we go. Then high to low. There we go. And that's a terrible drawing, but here's a much better drawing of what frequency modulation looks like. So essentially we have a pit that's the smallest size possible to represent a 1, and a pit double that size to represent 0. So yeah, it is. 1 is a short pit, 0 is a long pit, just the opposite of what you might hear. But we still have long pits and short pits. And so that's how it's encoded using frequency modulation. A little different from what you might expect. As you can see, a 0 might be a higher voltage or it might be a lower voltage. Now if you take a close look at this, you can see that each bit has a certain amount of space. I'll just call that a cell. You might call it a domain if this is on a magnetic disk, but we'll just call it a cell here. And notice that when we have a 0, there's a transition at the edge of each cell. So back to here, we see there's our cells transition at the edge of each cell. But if we have a 1, we have a transition in the middle of each cell. So we have a transition at the edge, transition in the middle, transition at the edge. So here's our cells. If I draw some dotted lines to show where the cells are. 0, transition at each edge. 1, transition at the edge and in the middle. If we look at it that way, we can make a modification of this FM whereby let's not have a transition. Let's take a quick look at this. So let's put our cell delimiters here. I'll have a better drawing in just a moment. So let's say if there's a 1, there's going to be a transition, but if there's a 0, let's not transition again until we get to another 1. Okay, so let's stretch that out a little bit. And if we have 2 zeros in a row, well, we got to handle that somehow. Well, if there's 2 zeros in a row, we'll have that transition. But then if there's another 1, let's wait until we get to that 1 to transition again. So this may look a little confusing, but here's a better look at it here. But notice that with the FM, we have this many transitions. With the modified FM, or modified frequency modulation, we have things stretched out a little bit. So now look at the smallest pit we are going to make if we use modified FM. The smallest pit we're going to make using modified frequency modulation is going to be twice the size of the smallest pit that the laser can read. So it looks like we're wasting space, doesn't it? Well, actually we are. So why don't we just shrink the whole thing down and take up less space? So notice that using the modified frequency modulation, we can fit the same amount of data into half of the space. So FM is a good logical way to do it, but MFM, modified frequency modulation, takes up half the space. Maybe a little confusing to see how it works, but the electronics doesn't care. We'll make the electronics that can read it. And that's how the first experimental CDs were made. They were made using MFM. However, there's even a better way. Let's change this to use what's called a non-return to zero code. In fact, we're going to use what's called non-return to zero mark, or NRZM. And what that's going to do for us, let's put some 1s and 0s here. 1, 1, 0, 0, 1, 1, 0, 1 for whatever. And so what we're going to do is we're going to transition from one state to another. Whenever there's a 1, transition, transition, but we're not going to transition at all for zeros. So transition, transition, no transition, transition. And off it goes. So this is called non-return to zero mark, or NRZM. And mark means that we have a transition when there's a 1. Now using this, our pits would be something like, there's a pit there, there's a pit there, or depending on whatever came first, let's flip this over just because we can, and say we started out low, change, change, no change, 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 no change, change. Now our pits will look like this. It could be either way depending on whatever data came before. So there's our pits. So here is the same data using the non-return to zero code. And what we can do with that is use another kind of encoding called run length limited. And what run length limited does is it limits the number of zeros you can have in succession. Because we can have a number of zeros in succession, and either have a code that goes something like, got to have a 1 first. There's our 1, a bunch of zeros, and another 1. There's 6 zeros in a row. We can make our electronics able to track a certain number of zeros before it gets lost at where the zeros begin and end. And let's use a code called 8 to 14 modulation. And what 8 to 14 modulation does is it takes every 8 bits and it uses a lookup table. So there's a table in the electronics that it can take these 8 bits and look it up and say, oh, that 8 bits is now turned into this 14 bits. I'm not going to draw that here, but I'll back up and you can see here that this 16-bit number has now been turned into these two 14-bit numbers. And holy cow, they're just taking up more space again. But look at what we have. Using this particular code guarantees that we'll not have any more than 10 zeros in a row. And it also guarantees that any 2 1s will always be separated by at least 2 zeros. So look at the length of the pits now. The smallest pit that will be made using this code is now 3 times the size of the smallest pit that can be read with the laser. So we can shrink this down again to the point where our final code takes up less than 1/3 of the space of our original FM code. So this is the code that's actually used to put the data on CDs. It's not, short for 0, long for 1. It actually modifies into this code that actually takes up less than 1/3 of the space, because every time we make a change, it stretches out those pits so we can shrink them back down again and squeeze that code into a much smaller space. So this little bit of code right here represents the same data that we started out with. 16 bits up here is now just this little tiny thing down here. So that's how the data is encoded on the CD, a little deeper into digital than maybe I want to at this point, but I think it's good to know, a little more than something that's wrong that's repeated over and over again on the internet.